by a hydraulics cylinder.
I got it. But I'm just saying, you cannot go very far.
You mean, yeah, this is kinematics, of course. Yeah.
Okay. I have the question about the diagram that we saw. There was a pulley pulling up the tractors upwards in the diagram. Yes, these pulleys, they pull the tractors upwards and then they go in the cycle. So installing these pulleys can also be the issue, and the technology is also delicate on the tractor. So what if the pulley breaks or something happens to it?
Yeah, there's a safety problem, of course. So first of all, the rope is mounted and the winch is mounted on the vehicle because of if you do it that way, the vehicle doesn't really move over the ground. So not the vehicle, the steel rope is not moving over the ground. So it's not so likely that the rope will break. That is first the reason why we mounted here. But second, we got two approaches how we want to do it. Here is not a safety brake like we thought about a thorn or something going into the ground which blocks it. And additionally, we want to steer into the plant because it's safer to destroy the plant and to drive into the plant than driving downwards and hit a vehicle or people or something. So we want to combine drive against the plant and also braking in terms of putting a thorn or something into the ground. Which
won't it destroy too much of yield if the object is too heavy? If the tractor is too heavy, won't it destroy the yield?
Yeah. So this is the point is what you are talking about is if this rope breaks. Huh?
Yes, the safety is there because mountains are unpredictable. There's always many quakes and always some tremors going inside the mountains, and we never know.
Yeah, but this vehicle approach in viticulture is already implemented since 5 years or so with chained vehicles, and in general there is no case where the rope was destroyed because of wearing, but because of misuse of the person. He drove too fast or something. But in general, these steel ropes are safe. So,
I have a question. You mentioned it is remote controlled or joystick controlled. So the remote control basically operates the machine or the winch itself?
Both. So in this case you have the winch. So it was in the controller where you can put up and down, and also you got left and right. In this case you got this differential drive, and it was combined that if you put left, the right wheel was turning on, and vice versa.
And I have another question that you mentioned you designed the winch yourself. So did you patent the design yet or not? Do you have any plans to patent it? Like it's your unique design, so any other cannot copy it, so something like that?
That's a good question. On the one hand side it could be possible, but to be honest, on the other side this winch is so expensive because we put all the work in it. It's not so likely that someone will use it. And this is, let me say, more a research winch.
Okay, thank you very much.
Okay, thank you.
That's a very interesting talk. With that, we come to our last speaker of the evening, Mr. Joerg Husemann. Brief introduction. Joerg Husemann studied computer science at the Technische Universität Kaiserslautern, focusing on embedded systems and robotics. After finishing his studies, he continued his research as a PhD student at the Robotics Research Lab. His research focuses on the navigation and cooperation in vehicle fleets. So, Mr. Joerg Husemann.
Okay, so good evening everyone. So thank you for the introduction. So my general topic is about planning and cooperation in multi-robot systems. So we still stay in the commercial vehicles, but now we want to look at systems where we have multiple robots, theoretically also of different type, which want to work together with each other. For that I will shortly start with a project which was already running during my master thesis, where I also participated and also worked like the first year, where it was about autonomous street construction. And then I want to take a look forward to some different scenarios, for example for soil compaction, where we have much larger areas and a much wider variety of vehicles. So typically for road construction you have a paver, which is here the vehicle in the background, which is spreading asphalt. And then you have drum rollers, which are compacting it. So in that image it's only one, but typically you have also multiple ones. And up to now those tasks are always done by humans, and our aim in the project was to automate the compaction behind the paver. So we wanted to have autonomous driving drum rollers in the end, which can automatically drive different tracks. And for that we had a localization system on the paver. Here on the left it's an image from the simulation. Later on I will also have a video, or short video of the real machines. And we tracked the position of the paver. We knew how wide the road is it is constructing. And then we are creating different tracks, which is shown here in the upload limit. So each of those areas are tracks, and we also split them after a certain distance. So they're typically between 25 and 50 meter long. And then they are also overlapping, because we don't want any areas which are not compacted in the end. So which also means that one vehicle is driving here on the outmost track. No other vehicle can drive on the track next to it, because there would be a collision in the end. Then we had some properties which we have to consider. One is the velocity, because there are velocity ranges in which we can drive on the area. For lower temperature. For lower temperatures we don't have any effect on them, because they are too cold, it's too hard already. And for too high temperatures we could completely destroy the road, so we also have to wait a bit before starting to drive on the ground. And those temperatures are can be measured on the paver in the front, and they can also be measured by the rollers when they drive on the area. So in the beginning we know the initial temperature. We have a rough model which estimates how fast the temperature is decreasing. And when driving over the asphalt, we can also measure the current temperature, so we get an update as soon as we start driving there. And then we have some measurement for the compaction. There we had two different methods. One is for the simulation, we just counted how often we drove on each area, which is shown here. So the red area means we didn't drive at all, and then it goes in the color range to green, which means it's fully compacted. So for the simulation, we typically say we want to drive on each area 4 times. In reality, we never did that in the end, but it's possible to measure the compaction also with a drum roller. So there we could take the real values to update the map. So maybe I start with the video and explain a bit during it. So that's one test in simulation. So I think the speed here is 8 or 16 times the normal speed, because typically vehicles drive with, I think, up to 5 kilometers per hour, so really slow. And you can see we evaluate the tracks based on the compaction and the temperature, and we give like a priority value to them, and then we assign them to the different vehicles. And as soon as it's finished with driving, or almost finished with driving, we look for the next possible track, and once again assign it to the vehicle. And then some tracks are blocked because of vehicles already driving there. And we also have some cases where we say we want to compact 2 tracks in a row, just to save the time for maneuvering to the next one. And here you also see one of the big advantages of the simulation, because it's possible to just start it and let it run for, I think the longest ones were like 45 minutes. And if something crashes, you can just restart and preserve why it happened, which is not that easily possible in the real scenario in the end. And I think that was like 1 year during my, after I was 1 year in my PhD, we also have a final presentation of our project. We also have some other co-workers, work of other co-workers was involved here. So we had 2 of our drum rollers set up with different sensors. So in one scenario we used GPS for localization. Here in the final presentation we used a LiDAR sensor because we were inside of a hall. So we just used the structure of the hall and an iterative closest point algorithm to compare our point clouds and some reference point clouds, and by that calculate our position. And we had 2 scenarios. In one, a driver drove forward and had to press a button, and then the machine was, so while driving forward, the machine was recording the points where it was, and backwards the driving was autonomously. In the second scenario, we did it completely autonomously, so we had the area of the street, and as in the simulation, the rollers were splitting up the different tracks and driving fully autonomously. I think in the end we had like a test run where they drove like 10 to 12 minutes without any problems, where we had to stop. But obviously we were always standing next to machines with emergency stop, so it's not that trustworthy that you would just drive without observing. And that paper was driven autonomously, so where we, not autonomously, it was driven manually, so where we didn't do anything. And then we had some of the stuff with Axel, which Axel introduced in the beginning. So we had our reaction framework, which has some things implemented for safety stop, which I think we also saw here in the beginning, where a person could walk sideways to the vehicle, and it's here, like here, and it's automatically stopping if he gets too close, and as soon as he leaves, it's starting again to drive. So, and we had actually that worked quite nicely. But a few days before the presentation were very stressful. Okay, so now let's forward to the ideas I'm currently working on. So I did, for example, that splitting up of a task I did do during my master thesis. And the idea was to go on with that idea of robot fleets and to split tasks between them and let them do bigger tasks in the end. And so we thought of some different scenarios which are a bit more complex, because for the drum roller thing we only had like a fixed area which was quite small, like maybe 10 meters of width and a length of a few hundred meters in the end. But always just a local area of 50 to 75 meters which has to be considered. So we thought of, first of all, we thought of that scenario here, which is soil compaction. So we have a large area which could be a parking lot. So in this example, it was given to us from the company we worked with, which was the creation of the Istanbul airport. So you have a gigantic area, which is in that case more or less flat, and you have compaction works on it. So in that case, first of all, ground compaction. So you want to have an even area in the end where you later on can put asphalt and so on. And here you have much more things to consider. So one advantage is you don't have, it's not that critical in terms of driving, because for the asphalt, if you do sharp turns, you quickly destroy the ground, which was also something the project before we didn't really manage to solve, and we always had problems with steering. So if you would do it on real asphalt, quite often would have failed. And yeah, so here those criteria are a bit less, but instead we have much more vehicles, different vehicles, and also a lot of different tasks. So also the order of the task is different and so on. So first idea was to take such a large environment and take like creating a data structure to work with it. So we had here a compaction grid map in the middle. When we do some kind of decomposition, so we split the area into different sub-areas, which then should be scheduled, given to the vehicles, and the vehicles have access to the map, so they can load the submap they should compact at the moment, and they are then able to upload the map and send it back to the server. So at the end we have one model of the environment which is always updated by the machines. Okay, so for splitting the area, the first test were done on a typical grid map, and just a more or less well-known approach. So you sweep from left to right over your grid map, everywhere where an obstacle starts or finishes, you split it into different cells. So here each color represents one cell. And then you can merge them in some cases. For example, here you would say, okay, that cell here is too small, I will merge it to a neighboring cell. And in the end you get areas which can be driven without static obstacles inside. So here the black area is an obstacle. So we can say the areas we created are obstacle-free, except for obviously people, cars going around or stuff which is manually placed there. So we, at least from the environment, from the static environment, we expect that the areas are free. And then the idea is to have run on multiple vehicles where we create some trajectory or target points, which is done here in an example, and then the vehicle should just drive them autonomously. So a similar thing with those points we also did in the asphalt scenario, where we always looked at the track, calculated some target points, and then use control of a vehicle to drive them. That's a different approach also created for such cells. It was more or less an experiment which, as you can see on the left, didn't really succeed. So the idea was to take a fully distributed approach. So we have an area, we take vehicles, and just say, take your local environment, what you can measure, and drive what's most suitable for your current situation. So it's a bit hard to see. We have here called tentacle approach. We have some possible trajectories, and we map them on the grid map and look where the compaction is the lowest. And based on that, we decide which trajectory we choose. And then we just do it all the time until we have some thresholds, say we have a maximum time we will drive, or we have reached a specific compaction value. But then, as you can see on the left, it's extremely chaotic. So sometimes the vehicle stands at a point, sees on, for example, it could be right here, and now it decides, okay, I drive to this area, and as soon as it's done, you only have finished area in your region, and then it's more or less confusing, just randomly drives around. And we also tried to tune it a bit with some heuristics, like we say, look in the map and find a point where it's not compacted and so on. But for the real world scenario, that's not really usable at the end. So at least we didn't manage to tune it so that it's as good as a simple approach where we just move up and down and always move it to the side. So, but the general idea of that cell compaction seems to be to work quite well. But now the idea was, what is if we have a more complex scenario? So here we have an image of landfill close to Kaiserslautern. And typically here you have trucks which drive up the hill. They throw down the material, and we have machines which drive the slopes and compact them. And that's more or less happening the whole day. In the beginning, the area here was a canyon, and now it's more or less like a hill. And now we wanted to consider those more complex environments, because in the first thing we just had a flat area, we use a 2D map, and we're happy. In this case, it doesn't work anymore, because we have to consider those slopes. We have to consider the utilities of vehicles. So some vehicles are able to drive the slopes, some might not be able to do it. And we also have to consider that the environment is changing all the time, because after some days our hills are larger, the slopes could change. So we want to take all that stuff also into account. And that's actually the work I'm currently working on. So I also looked into some previous works. For example, also for agricultural use cases, some stuff exists where the area is mapped, the 3D area is mapped to a 2D map, and trajectories are calculated based on the 2D map. Can be seen here, it was for some kind of field, not sure if it was a vineyard or something else. So where I try to calculate, to map it to the 2D case, but calculate trajectories in the 3D case. And my current work is on, okay, that's the general aim, so I want to have the composition of environment, so splitting up based on the different types of environment. So do I have a flat area, do I have slopes? And then I want also to group them together to have larger environments of one type more or less. For example, also for the slope, the orientation of the slope is relevant and the steepness. So where I want to have some kind of segmentation, which area is of which type, to later on decide what vehicle is capable of doing the tasks. And there could be also some additional tasks like earth moving, so that maybe later on should also be considered. When later on, obviously, the idea is assign suitable tasks, as it was done before, and also select driving strategies based on the environment. For example, slopes have to be driven in a different way as a flat area, or in a more restricted way. Yeah, that's what I'm currently working on. So the aim is to find the data structure in which we can describe those environments. And here on the top, there's one example for a city with a 3D voxel map, so more or less like a grid map, but in 3 dimensions. So we have cubes instead of cells. But what I'm currently trying to do is to have such a map as here shown at the bottom, which is also a grid map, but in the cells are described by the normals of the ground. So in case of a flat ground, my normal is always pointing upwards. If I have a slope, the normal is pointing outside of the slope. So based on those normals, you can decide in which direction your area goes, and if you compare the normals of neighboring cells, you can also create larger shapes of a specific type, so a slope in a specific direction of that area. That's something which I currently want to use. So you have like a point cloud, you put your points into a cell, and then calculate the orientation of the ground in the cell, and then merge them together to get the segmentation of the area. That's a bit off topic, which was a master thesis of a student I was supervising, but which also somehow fits into that whole idea in the end, because it was about the scheduling. That's now a bit off topic because it was about the autonomous bus we have in our group. But the idea was we have, I think, on an environment of a campus plus some additional areas, we have a lot of buses. So in our case, we have up to 10 buses with a seat capacity of 6 or 10 passengers. And the idea is that we have different requests which we want to assign to the buses. So we look how the bus can drive, where he can pick up someone and drop him off again. It was completely random where those requests can be spawned. So I later on have the hope that I can also transfer this idea. So the scheduling of people to buses is more or less also usable to schedule tasks in our environment to my rollers. There's also the idea to later on use that approach in the soil compaction scenario. But I just want to quickly show it, but don't want to go into details. So that's actually it from my side. So maybe just as a short summary, so we have that asphalt or road compaction scenario or project. And currently there's the idea with a mapping server using such a soil compaction scenario. And yeah, that's the last picture is like the next work I'm currently doing. Thank you.
Any questions?
I wanted to ask that are these machines are communicating with each other? There are like multi-agents working in the environment?
So in our road construction scenario, the map was created on the paper, and the machines were communicating with the paper. Also where the decision was made, where they should drive, so just the track, and they were calculating the target points based on the map. So the machines were not communicating with each other, but one machine was deciding. We also thought of everything communicating with each other, but then it gets way more chaotic and much more things to consider. So that was the easier approach.
Thank you.
Yes?
As we saw in the technical approach, some areas were still left out. So in the simple scenario of roads, were there some problems like any area is left out, some areas are just not being visited due to their small size?
Actually, so in some cases, something wasn't finished because of a constraint of the temperature. So it took too long, so the road was too cold, and we couldn't continue compacting that. So that happened. But we didn't use the tentacle approach in the road construction. Instead, we just had target points. And since those tracks are overlapping, so we had an overlap like 20 or 30 centimeters, it's not critical if we drive a bit too much to the left or right, because from the other track it was still compacted. So there we didn't have the problem that areas were left out.
Yes, so when we are picking data points, how are they picked? Are they picked on the basis of their slope or something? Or is there a when slope is not there, what is being used to pick the data points? And when it is there, then what is being used?
Okay, so the road construction,
Yes,
we had those
when we are
tracks.
taking the data points,
Yes.
is it mapped like completely, and then we see which points are covered, and then we stop taking them, and or is it just like the machine does it by itself? It
You
takes
mean
the points in its immediate vicinity, and then it covers those, and then it moves forward.
Do you mean now for the road construction or for the
Both,
technical?
in all cases.
Okay, so for the road construction we had those tracks, and we just took the target points were in the middle of the track, and then you had to do a turn in where we just selected the point which is a bit to the side. For that tactical approach, those tentacles are pre-calculated. So we have one for driving straight, we have one for driving 1 degree steering angle to both sides, and so on. And where you can just map the cells which will be covered when driving that trajectory. But in that case, it's the case, so you don't drive a full trajectory, you just drive like a second or something, then you select the again the next best trajectory
Next path to the data point.
And that's also because it's completely locally and you don't really plan it, you have a problem that some areas are left out.
So it's not completely autonomous, there is some programming involved in it, hard coding involved in it.
It's not hard coding, so you just look which cells on the grid map, so you look into the radius of the cells, and by that you evaluate, so you know one tentacle has those 10 cells, you can look into the radius inside, and decide this trajectory is compacted to 50%, for example, on average. And another tentacle is compacted 80% by average, and then you decide for one which is less compacted. Also considering obstacles, then we would say, okay, here I have an obstacle after 20 centimeters, I will drive somewhere else. Yes?
So in an environment like this where multiple agents are working synchronously, if one of the agent is not behaving as it should, how much does it affect the behavior of the other agents?
Okay, in the larger environment, so the soil compaction, I say it's maybe less of a problem. In the road construction, it's really critical. If you have a vehicle standing still in your road and it's cooling down, you have to extract it and start again, more or less. Theoretically, so we never used it in the real road construction because for that it wasn't good. There's a lot of more development required for it. Theoretically, we always have the option to drive it manually by a joystick, so if something machine really fails, we are still able to remove it and maybe have another machine, or you have to slow down the speed of the paver to let the remaining machines, so to enable the remaining machines to finish it. If it completely breaks down because then you can't drive it anymore, you can't solve it, but in reality if your machine breaks, you also can't really do anything. Then you just have a big problem.
Okay. So thank you very much. I would like to thank our esteemed guests from Germany here for their nice talks. I think it was very exciting or interesting, and all of us, probably most of us were here, enjoyed also here. So with that, I think we should conclude this workshop. I would ask whoever has this attendance, please hand it over to me. Yeah, after this workshop. Okay, thank you very much, everybody. Yeah, that's it for today.